Hello, I'm Annabelle, and myself along with Hannah, Julia, Sunny, and Vishva are here to present the mechanics of blowguns. Blowguns have been around for centuries, dating back to 265 AD. They were used across the world as hunting weapons for small animals, where they would dip the dart into poison to paralyze the target. Typically, the gun and dart were made from natural resources such as wood or bamboo.
We explored what barrel length and dart position are most effective in the blowgun. Our darts are made of a nail, post-it note, hot glue, and tape. The nail provides weight for momentum, while a post-it note cone is wrapped around the nail to catch the pressure that drives the dart forward. The dart exits the longest blowgun faster than the shortest because the dart had more time to accelerate within the blowgun barrel.
Configuration 1 was with the dart located at the far end of the blowgun barrel. We controlled our dependent variables by maintaining a constant starting height and maximum lung capacity with a consistent operator. However, we still had inconsistent results because the darts tumbled out of the blowgun. In configuration 2, the dart started at the mouth of the blowgun. This allowed the darts to stabilize before they exit and resulted in them going significantly further with a stronger linear relationship as the r-squared value was much closer to 1.
We devised a mathematical model using Bernoulli's principle and a force balance to calculate exit velocity. To solve for the exit acceleration, drag force and kinetic friction are subtracted from the difference in pressure force acting on the dart. Since the air inside the blowgun travels along a streamline, this pressure difference can be safely assumed from Bernoulli's principle. The results from configuration 1, where the dart was placed at the end of the barrel, yielded consistently shorter distances than configuration 2. This is due to the delta x term in the exit velocity equation, which refers to the distance traveled by the dart inside the gun. Since the dart is placed at the end of the barrel, it will have a small delta x, yielding similar exit velocities and distances traveled at each barrel length.
For configuration 2, the dart was loaded at the mouth of the blowgun. Delta x was the same as the blowgun length. This created a relationship where the longer the tube, the greater the exit velocity. Thus, using a longer tube resulted in further distances traveled by the dart. The dart also experiences the force of air for more time in the longer tube, thus generating a faster exit velocity. Drag and friction introduce losses that explain the nonlinearity seen in our data. The longer tube has more drag due to having more time in the tube for air to recirculate. However, note that a linear trend line still had a decent fit of r squared is around 0.974, so at this length, friction and drag forces are minimal. Overall, the data showed that when loading the dart into the mouth of the blowgun, the longer blowguns were more effective due to a larger displacement which created a larger exit velocity. To be effective, the dart must be loaded into the mouth of the gun, as loading at the end has a minimal displacement and thus a small exit velocity. Drag and frictional forces are minimal up to any realistic length, as they would only have an impact on an inconveniently long blowgun. Thanks so much for watching. We will now demonstrate and answer any questions.